This video is the 16th in a series of pure factual recall questions to allow you to prepare for the Assessment Objective 1 type questions in A-level chemistry. These make up 30% of the available marks. This video is for the first Year 12 organic chemistry topic. There's a link to the questions in the description below so that you can try them out and then use this video to check your answers. The organic chemistry topic starts with some different types of formulae. So empirical formula is defined as the simplest whole number ratio of atoms of elements in a compound. For instance, if we were going to take an alkene like butene, which has the formula C4H8, then the simplest whole number ratio would be 1 to 2, and therefore the empirical formula would be CH2. In contrast to that, a molecular formula tells you about one particular molecule and gives you the exact number of atoms of each type within that molecule. A general formula is for the whole of a homologous series, and it tells you what the algebraic ratio of the different elements in it is going to be. So for instance, if we think about the alkanes, then it will be CnH2n plus 2. Next, we think about structural formula, displayed formula, and skeletal formula. And here as an example, I've picked pentane, which is C5H12. So in the structural formula, we're taking that molecular formula and breaking it apart into sub-pieces so that we can see what's actually connected together. So here we would have CH3, CH2, 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 CH3. Our displayed formula is a full diagram showing where every atom is and what it's bonded to. So we start with our chain of 5 carbons, and then around each of those we're going to add the hydrogens in. For a skeletal formula, we still have the shape, but we have slightly less detail because we assume that every corner is a carbon atom and we assume that those are fully saturated with hydrogen unless we say something different. So here we're just going to have 4 little lines making a double upside down V. Structural isomers contain the exact same atoms as each other, so therefore they have the same molecular formula. But those atoms are arranged differently to one another. So for instance, if we carry on thinking about pentane as our example, then it has structural isomers like methyl butane and also 2,2-dimethyl propane. There are actually 3 different types of structural isomer. We have chain isomers, like these ones, where the length of the longest carbon chain has changed. We also have position isomers, where the functional group is in different places along that chain. And we have functional group isomers. This would include things like aldehydes and ketones, where they both have that oxygen atom double bonded in, but it's in different places, and therefore it's a different functional group. Stereoisomers have the same structural formula, but those atoms are arranged differently in space. So the easiest examples to think about are ones which have 4 completely different groups bonded around a carbon-carbon double bond, like these. In order for a molecule to have EZ isomers, it firstly needs to have that carbon-carbon double bond, because this is going to be unable to rotate. Then it's going to need 2 different groups attached to either end of that double bond. To work out whether we're looking at an E isomer or a Z isomer, we need to look at both sides of the double bond independently, and we need to assign priority based on the atomic number of the atoms that are attached. The difference between an E and a Z isomer, in other words, entgegen, which means apart from each other, and zusammen, which means together, is about whether the highest priority groups are on the same side of the double bond. So if it's an entgegen isomer, you have your priority groups on opposite sides, whereas if it's zusammen, then it's priority groups on the same side. In this example, we're going to say that chlorine with an atomic number of 17 is obviously much higher priority than hydrogen with an atomic number of 1, and likewise iodine with an atomic number of 53 is higher priority than bromine with an atomic number of 35. Since both of these high priority groups are on the same side of the double bond, this is going to be a Z or zusammen isomer. Just like at GCSE, a hydrocarbon is going to be defined as a molecule or compound that is made exclusively from hydrogen and carbon. So this includes our alkanes and also our alkenes. A saturated molecule contains the greatest possible number of carbon-hydrogen bonds. So there are no carbon-carbon double bonds and no carbon-carbon triple bonds. A homologous series, like alkanes or alkenes or alcohols, is a group of compounds that has the same functional group and general formula, and this will lend it the same chemical properties. When naming a particular compound, we need to be aware of the order of priority. So first up we have the carboxylic acids, followed by aldehyde, ketone, alcohols, alkenes, and finally halogen atoms. The suffix ane, like butane or decane, tells us we're dealing with an alkane, whereas ene shows us that it's an alkene, and ine shows us it's an alkyne. Ol is the suffix for an alcohol, whereas al is the suffix for an aldehyde. One is the suffix for a ketone, and oic tells us we're dealing with a carboxylic acid. Hydroxy tells us that we have an alcohol group or a hydroxy group, but it's at the start of the molecule because we have a higher priority suffix that we need to deal with. Formyl tells us that we're dealing with an aldehyde, but again, this is not the highest priority functional group, so formyl is going at the start as a prefix as opposed to al at the end as a suffix. And oxo tells us that we're dealing with a ketone, but again, we have a higher priority functional group. A free radical is an atom, molecule or ion that has a single unpaired valence electron, and we denote this using a single dot. Free radical substitution of methane with chlorine has 3 steps to it, so we need to think about initiation, propagation and termination. In the initiation step, UV light is responsible for the homolytic fission of chlorine molecules. So homolytic fission means that the bond is breaking and it's breaking evenly. So both of the atoms in that molecule are getting one single unpaired electron, and that's why we have 2 free radicals. These are then going to attack methane, and this is going to lead us to have hydrogen chloride formed and also a new free radical. This free radical in turn can attack chlorine molecules. And so we're left with chloromethane, and we also regain that chlorine free radical. So the chlorine free radical is acting as a catalyst because at the end of this it's still being reformed. Termination will occur when either 2 of these chlorine free radicals meet up to produce a chlorine molecule, or when 2 methyl free radicals meet up to form ethane. Or we could have a single chlorine free radical with a single methyl free radical joining together to make chloromethane. Thanks very much for watching, and I hope you found this a useful video as you prepare for your A-level chemistry exams. If you did find it useful, then don't forget to like, subscribe, comment and share the channel, and I'll be back soon with some more A-level chemistry videos.